Hi, everybody. My name's Ben Bowers, and I'm an assistant professor at Auburn University in the Department of Civil and Environmental Engineering. Some of you all might recognize me, though. I actually spent 4.5 years working at VTRC as a research scientist. Very much miss Virginia. Hope to get up there again soon. But I am loving life down here in Auburn as well. So I'm excited to talk to you guys today about something that's very important to me, a big part of my program, and something I was definitely involved in a lot when I was up in Virginia. And that is cold asphalt plant and cold in place recycling mix design. So many of you guys have probably seen some of the other trainings on kind of what is cold recycling, where is it used, but just in case you haven't, I want to give you a quick refresher on what cold recycling is. So it's by definition a series of processes where the existing paving materials can be reused in a new or rehabilitated pavement structure. So what we're talking about here is going in and recycling 100% of the wrap and putting it back into a new base layer. Now, there are two major types of cold recycling. The first one is cold in-place recycling, and the second is cold central plant recycling. Now, cold in-place recycling is what it sounds like. You're going to go out, and this is a single unit train. You might have multiple unit trains. You're going to go down the road and you're going to pulverize the bound layers. So we're not getting into the subgrade or the aggregate base. We're going to pulverize just the asphalt in place, add a little bit of asphalt binder or a recycling agent in the form of foam or emulsified asphalt, maybe a little bit of an active filler like cement showed up here in gray in front of the truck, and also water, which we'll talk about here in a second. Now you'll notice it comes out the back behind the screed, looking nice and black like a typical asphalt pavement. We're typically going 2 to 5 inches thick, and we're just going to come back and roll it and then put a surface mix on top. Now, cold central plant recycling, or CCPR, very similar product, but the difference is we're not doing it in place. What we're going to do is we're going to take the material out of the road, or we're going to use existing wrap piles. So this is great for those of you who have a lot of wrap on site. Because you can use it for lane additions and things like that. We're going to bring the asphalt material or the wrap to this mobile plant that can be set up near the project, can be set up in the yard at your hot mix plant. And we'll use that existing wrap to make a very similar mixture to what the cold in place recycled mix is. Now, typically here, we're going to do 4 to 6 inch layers when we take it out to the road. And we can also put multiple lifts in because we're not doing it in place. So we can haul some material out, compact it, and then put another lift on top. Ultimately, we are going to need to surface it though, just like CIR. So just to kind of walk real quickly through the CCPR process, this is the process that's been used, at least on the largest projects, the interstate projects in Virginia, both I-81 up in Stanton, as well as I-64 out near Williamsburg. You'll see here, we're loading the wrap into the KMA, which is a giant pug mill. It's going to add the binder and the water to it and mix everything up. Now it goes up a conveyor and is ejected at the end of the conveyor. Typically, you would pull a truck up here and load it just like you might if you were loading straight out of your hot mix plant and not utilizing a silo. However, the alternative is that you can pick it up with a loader and load it into the truck that way. And so that's what's being done here. Here you see the material is taken out to the job site and it is loaded into a kind of a standing paving equipment, typical paver and screed. You can see here we are just running down. I think this is I-81 up in the Stanton district. These photos are courtesy of Dr. Brian Diefendorfer. And then finally, we're going to roll the mix. And, the VDOT specification, last I checked, it does require a pneumatic roller. I think it was a 25-ton and a steel roller as well. So you can see the rolling process, very similar to what you're doing with hot mix. So the benefit of these processes is that we're able to use our standard paving equipment to place them. So, what exactly is cold recycling? It's a method of reconstructing pavement using 100% recycled material, as I said earlier. It's a combination of wrap, water, which always throws us for a little bit of a loop, but this material does have an optimal moisture content. Keep in mind it's cold, we're not heating it up, so we're not activating that binder, that wrap binder on it. Typically around 2 to 2.5% asphalt binder in the form of a foam or an emulsion. Less than or equal to 1% active filler, which is maybe cement or lime. And this is used to get you a little bit of early strength or some long-term strength and stiffness so that you can open it up to traffic. That's what that early strength's for. It's also used to help the fine material, helps to disperse the asphalt bubbles and the foam throughout the mixed matrix as well. You may include an inactive filler, which is an aggregate that can be used for gradation correction. Some states, I think Virginia is one of them, allow up to 50% of this inactive filler in there as well. Now, the key here is this is a hybrid material. So this is not hot mix, and it's also not aggregate based. So here what we're doing is really merging two worlds. So kind of the geotechnical world where we're doing subgrade stabilization or aggregate based stabilization, and our hot mix world where we're using asphalt, we're using hot binder or an emulsified binder to stick things together. We're placing it with an actual paver and we're rolling it very similarly. So it is a hybrid material. It's somewhere in between the two. That's an important thing to remember the first time you get out on a job site to place this material or the first time you use it in the lab. So I think it's helpful to think a little bit, especially since many of you guys work in the hot mix industry, about how cold recycled mixes are like HMA and how they're not. So it's like an HMA in the fact that it provides a flexible base material. It's viscoelastic, which means it is affected by both load rate and frequency as well as temperature. It softens, it stiffens based on whether it's hot or cold. It does contain asphalt binder. And I'm not just talking about the wrap binder. Obviously, that's in there and that contributes to that viscoelasticity, but also the foam or emulsified asphalt binder, which we call in cold recycling the recycling agent. That is not to be confused with rejuvenators. We are not using rejuvenators here, which are also sometimes referred to as recycling agents. Recycling agent here is a foam or emulsified asphalt binder. It can be placed using conventional paving equipment. As you see here, this is the I-64 project out near Williamsburg. And then our performance tests we use for approval are either the indirect tensile test or the Marshall stability test, which are tests that you should be familiar with from hot mix. Now, how is it not like hot mix? First and foremost, and this is the one that always trips us out, because we know in hot mix asphalt, water is bad. We do not want water near us. We want to get it out of our aggregates and the drum, things like that. It can throw everything off. Here, we want water. So we add water to achieve an optimal moisture content or an optimum density. An active filler is often used to help with that strength, that early strength and stiffness, and this is lime or cement. We recommend to focus on density, not air voids in design and construction. And that's largely because of the variability in the wrap can lead to faulty air void estimates. So density just seems to be more consistent. Folks who have been doing this for a very long time, this is not new technology, have been using density, which again, kind of references more of that subgrade or aggregate based soil type approach. We also allow this material to cure before placing the overlay, and that's typically through the reduction of a moisture content, or in some states, it's a specific amount of time. I'll also draw your attention to the fact that this material looks really dry. You can see it's kind of gray. This material specifically, I believe, has around 10 to 15% number 10s in it, so it's got some of that inactive filler. It's also got cement. But you break it open after the indirect tensile, and you can see where, yes, it is in fact asphalt that is in there. So before we really get into mix design, we need to talk a little bit about the materials that are used. We're going to go and talk through wrap. We'll talk a little bit about aggregate when necessary. Water, notice I say what, because that is such an uncommon thing for us. A small percentage of active filler, which is that lime, cement, fly ash, or et cetera. And then the recycling agent and the specifics about the recycling agent, which is that foam or emulsified asphalt. Now, gradation, the wrap itself. This is a little different too from hot mix. Our wrap gradation is typically going to be based on a black rock gradation or a wrap gradation. So we're not going to go and take a sample of wrap and burn it and then take the aggregate that's left over after we incinerate all of the asphalt wrap binder off of it. We're not going to then take a gradation there. What we want is the gradation of the wrap. And that is because what we're going to actually be placing out there is that wrap itself. That is the granular material we're using. Now, gradation bands, target bands are used and provided by Wirtgen in 2012. They have the reference is from 2012. It's a manual. That is typically what we reference, though it is not always referenced. And I'll show you that here on the next slide. CCPR, we typically design make one design based on our wrap material. We typically know, and on the projects I've been on, typically we're using stockpiled material, so it's already been crushed and processed. We can pretty much count on the fact that that gradation is not going to change a whole lot, so we just do one design with that gradation material. Now with cold in-place recycling, of course, what we're doing is we're going out and we're pulverizing an intact road in place. And so you can imagine the gradation is going to change some, and it may be hard to perfectly replicate what the milling head or the recycling head is doing in the lab. So typically what we'll do here is generate a coarse design and a fine design. So we'll make a coarse gradation and a fine gradation for that design. And that's because typically the way we'll get that material is either we'll take coarse and crush them in the lab from the pavement we're going to recycle, or we'll go out, we'll grind some of that material up or pulverize it and collect it and take it back. The problem there is then you have to patch it, right? So what we'll do is we'll take that material, we'll create a coarse gradation and a fine gradation and do the design. Now we know our recycling equipment can provide a consistent gradation, but it may not be perfect. So we know if we do a coarse gradation and a fine gradation and know how much virgin binder or recycling agent we need to add to get our strength targets that we need and what the densities look like, then when we get out into the field, we're likely going to be somewhere in between, and so we can make appropriate field adjustments. These mixes are typically pretty forgiving, and so it doesn't usually take a major adjustment to hit your targets. And that's something once you get a little more experience, you'll start to see. So here are the recommended gradations from Wirtgen. You'll notice here we have, they show what kind of a typical wrap or a typical gravel are. Your target gradings are right here in black. You'll also notice there's a little bit of a bulge that you want to try to avoid here between the 2.36 and the 200 sieves. So you want to try to avoid hitting that bulge right there. But you typically want your gradings to be in between. Now I will tell you that I have worked on projects where we're a little bit fine. We still have been getting good performance. So their key is really, that's something you would need to get approvals on and things like that. But the key is to make sure that you hit your strengths, which we'll talk about here in a minute. So we've got our gradation. The next thing we're going to do is we're going to establish our optimum water content. Like soils and aggregate, wrap has an optimum moisture content, as I alluded to a second ago. So we're going to use AASHTO T180 to establish that moisture density relationship. Method D, this is what we use for soil material passing the 19 millimeter sieve. You guys use that 6-inch diameter by 4.5, roughly 4.5-inch tall mold. Use a 10-pound hammer and an 18-inch drop weight, and you layer it in 5 layers. So you can establish that optimum water content, which is going to give you the maximum density. The next thing we think about is an active filler. Now, you don't always need an active filler. Hydrated lime and cement are the most frequently used active fillers. And these active fillers help you do a couple of things. One is if you're going to see here in a second, we're going to do dry strengths and wet strengths. So it can help you hit your wet strength if you're failing. And again, it can also get you some of that early stiffness so that you can put traffic on the route a little bit quicker. And in the case of foam, it gives you a little extra number 200 material to help distribute those foam bubbles throughout the mix matrix. Now, it's recommended to use 1% or less. And the reason is because you start getting above 1% and you start getting concerned that you're going to really embrittle the mix and potentially cause cracking. So we want to try to keep it around 1% or less based on experience. Now, the benefits of this are, again, it adds fines to the mix for foam mixes to help distribute the foam bubbles. It helps when failing wet and dry strength ratios, gets you that early strength. And we found in our NCHRP 952 project, which was work out of the University of Maryland and VTRC, that you get long-term strength benefits as well. So that is helpful. Now the recycling agent, remember, we're not talking about rejuvenators. We're talking about foamed asphalt or emulsified asphalt. Those are the two that we use. Now you choose foam versus emulsion typically based on a few factors. One is availability. What do you have access to? 2 is often preference. What are you the most comfortable with? And 3 is, in some states, the type of job and or the rate at which it must the pavement must be open to traffic can cause you to choose an emulsion or foam. If you choose an emulsion, you need to worry about break time. However, you can work with your emulsion supplier to ensure that you get an engineered emulsion that will break at a rate that is appropriate for the job. So you can always work with your emulsion supplier. So if you have a good relationship with them, I would recommend you talk to them if you're going to do one of these jobs. Now, the grading of your binder, your PG grade is based on LTPP bind at the 98% reliability at the depth of the top of the CR layer. Now, for foamed asphalt specifically, you must ensure that the binder exhibits appropriate foaming properties. So you want to look at the expansion ratio. This is a measure of the viscosity of the foam bitumen. So basically, when you add water to it and it's hot, it's going to expand. And so you want to make sure that that it expands enough, that it's going to expand so that it can distribute throughout the mixed matrix well. The second thing you're worried about is the half-life. And this is the measure of the stability of that foam. And that is basically the time it takes for the foam to collapse to half of its volume. So how quickly after it expands does it collapse? Now, it's really important for you to recognize that there are many binders that we have tested that do not meet the foaming and half-life criteria. And in fact, I've tested a number of them that really don't foam at all. So it is really important to check these things. If your binder is not foaming, you're not going to get a good mix. So you make sure that both in design and when you get out into the field that your binder is foaming. So when we check our expansion ratio and our half-life, we can then establish our foaming temperature and our foaming water content. So our minimum expansion ratio is 8. Our minimum half-life is 6. So you can see here, in blue, well, first let's look. In blue, our y-axis here is expansion ratio. Our x-axis is our water content of our bitumen. So this is not the optimum for the rat. This is purely the water that's going into the asphalt binder. And you'll notice the more water we add, go figure, the more it expands. So that's great. We have a minimum acceptable expansion of 8 times. And you measure that using a dipstick that comes with the foaming apparatus if you were to buy one from Workin in this calibrated bucket here. You can see the foam being made here to test it. So a minimum of 8. Now, our half-life, as you add water, the half-life starts to go down. So it becomes less stable. It starts collapsing quicker. Our minimum acceptable half-life is 6. So basically what you're going to do is you're going to run this test at multiple water contents in the binder, and you're going to measure the expansion ratio and the half-life, and you're going to plot it at each of these water addition contents, and then you're going to look at where the minimum expansion ratio is here at roughly 2.3%, and your minimum acceptable half-life, which is roughly here at about 3.7, and you're going to go halfway point. So that's optimum water addition for this binder is 3. You'll also run this test at multiple temperatures. Typically, I've seen about 5 to 10 degrees. So maybe 165, 170, and 175. So run it at multiple temperatures, and you're going to get different properties when you do that. It's going to expand a little more or a little less, et cetera. So you want to zero in on these for your binder itself. Now, if you're using emulsion as your recycling agent, the general recommendation is a minimum residue of 64%, and this is from ERA. If there is a cationic emulsion being used, use a CSS1 or CSS1H from AASHTO M208. If it's anionic, you want to use an HFMS2 or an HFMS2H or 2S from AASHTO M140. You want to make sure you work with your emulsion supplier to ensure that you use the correct emulsion for the application. So make sure you're communicating with them. They want you to succeed, you want to succeed. So that's important. And then finally, if you are having to use cement as an active filler, you need to make sure it's not going to cause the emulsion to break faster, unless that's what you're targeting. And you need to be aware of that because you don't want to get out there in the field and construction lags a little bit and you realize your emulsion is broken already. So we have now gone through our gradation. We've established our optimum water content. We figured out, we're using a foam or an emulsion, what the properties are that we need. Now, how do we go about selecting an optimum binder content or bitumen content. Now, our typical binder content is going to be between 2 and 2.5%, but sometimes it goes as low as 1.8% of the mix. For foam, you're going to want to test at least 3 foam contents. You're going to run at each one of them, you're going to pound out a pill. You're going to check out your dry indirect tensile strength. And you have a minimum in many states of 45 PSI. I think VDOT just changed theirs to 53, which was based on some data that they collected or some analysis that they did. So anyway, you have a minimum you're going to be targeting. It could be 45, it could be 50, it could be 53. So pay attention to those specs. And then you're going to have a wet ITS as well. So you're going to run some saturated specimens, just like if you were doing TSRs for hot mix. Only here, we're going to target a minimum of 0.7 for that tensile strength ratio. Now for emulsion, you're going to run 3 emulsion contents, just like you did with foam. Only now we're not doing ITS as much. We're focusing more on that Marshall stability. We're going to look at a minimum 2,500 pounds at a 6-inch diameter or 1,250 for a 4-inch diameter pill. You're also going to run the wet Marshall stability. You need to retain stability of 0.7 or 70%, just like you do for the ITS. So we've walked through all kind of the elements of the materials. Now what I'm going to do is walk you through the process that we go through when we do this design. And we'll have pictures and things like that to accompany us. So this mix design process is described in one of these 4 AASHTO specifications, depending on whether you're using foam or emulsion, and how to select materials, etc. You can also look in the work in cold recycling manual, which is shown here, which is that 2012 reference I referenced earlier. I think there's a 2015 version now. Or you can look at the basic asphalt recycling manual from ERA. That's another great resource. I would recommend you look at all 3 of these resources, especially as you start to figure this process out on your own. So first thing we're going to do is sample our wrap and check gradation. If the gradation does not meet the specifications, we consider doing a few things. We can do some additional representative crushing. We can look at alternative wrap stockpiles or blends if we have other options on our site. Or we can look at the addition of adstone, noting that some allow up to 50% virgin aggregate. I've never seen anything that high, nor do I really know what it's going to do to the performance, but it is allowable. And if you go through the design, I would expect it will perform. So it is something that can be considered. Next, you're going to look at that moisture density relationship. So AASHTO T180 method D, you can see here, we looked at just under 3%, just under 4%, a little bit over 4.5%, and then about 5.5%. And in this example, about 4.5% is your optimum moisture content. That is typically around, if you didn't have this, I would say 5 is probably around where you're looking. So it can be a little above, a little below. If you get way outside of this boundary, I would run a second test just to verify. Then we're going to look at our binder properties. And I would recommend you look at more than 2 points. For the example I was able to pull, this is unfortunately what we had. You'll notice here we look at our expansion ratio here in blue, and that's plotted over here. So if our minimum is 8, we know that first set is not going to work, but the second does. If you look at your foam, or your half-life, which is here in orange, our minimum there is 6. So we come over here, we know that we need to be above that point right there. So what we chose was right here at 1.5% is the water content for this specific binder. So we met both the 8 and the 6 requirement. In terms of mixing, this is a laboratory pug mill. It's a Wirtgen device that is at VTRC. We have one down here at NCAT as well. Very useful for design. You do not have to use this for design, though. You can use a standard pug mill. What you're going to do first is you're going to add your wrap and any active filler if you need it. You're going to pulverize the mix and mix it up for about 30 seconds or so. Be consistent until it's uniformly mixed. Then what you're going to do is you're going to add the water on top of that to meet that optimal moisture content as established earlier through the Proctor mold. Now, make sure you also account for any water also already in the wrap. So you likely have a little bit of water in the wrap already. So make sure you factor that out. And that adds up pretty quickly, as you guys know. And then you mix for an additional increment of time until you uniformly mix, which is typically about 30 seconds. Now, once you're done doing that, it's a really good rule of thumb to reach in, grab a handful of this material, ball it up in your hands and let go. Now, if the wrap falls apart, then you know it's probably too dry. And so you really probably need to take a quick assessment of whether or not you have the optimum moisture content. However, if you start to squeeze water out between your hands, you probably have a little too much water in there. And so you might want to back off your water content a little bit. This is a very, you're using your calibrated hand and calibrated eye to check this, right? But it is a really good rule of thumb when you're doing these mixed designs to kind of validate what you've come up with. The next thing you're going to do is add the recycling agent. The example here is emulsion, so you can see they've already weighed out the amount of emulsion per weight by weight that you need, simply pouring it in. With the foam on this device specifically, it has a foaming nozzle and it'll inject the amount of material that you tell it to. Then what you're going to do is you're going to mix it again for about 30 seconds till it's uniformly distributed. You're then going to sample the materials and you're going to create your specimens. For the Marshall hammer, you're going to do 75 blows per side. If you're doing a gyratory design, you're going to use 30 gyrations as your target. The next thing you have to do, and this is very important in design, is the curing process. And you need to keep this very consistent. For emulsion, we cure at 140 degrees Fahrenheit to a constant mass, and then we hold it at 104 degrees Fahrenheit for 2 hours prior to testing. If we have soaked specimens, which we will have, we will vacuum saturate them to 50 to 65% in a 77 degree Fahrenheit water bath for 23 hours, and then we'll put it at 104 degree water bath for an additional hour immediately before testing. So that's the difference between our wet and our dry. One, of course, is going to be vacuum saturated, and the other, obviously, is just going to be sitting in the oven. For foam, we're going to cure it at a completely different temperature. So we're going to cure it at 104 degrees Fahrenheit for 72 hours. We're going to cool it to room temperature for 24 hours and test it. Our soaked specimens, we're going to do that 104 degrees Fahrenheit for 72 hours, but we're going to put them in a water bath for 24 hours at 77 degrees Fahrenheit, and then test them immediately after we pull them out of the bath. And here you can see we've run our indirect tensile test. So you run all of these breaks, you run your calculations, you make sure that you're passing your minimums and your wet strength. And so what you see here is this is at a 45 PSI for this design. You see our dry strengths. We tested at 2% here on the x-axis, 2.3% and 2.6%. You see our ITS strength here on the y-axis. And for all of them, for our dry strength, we were passing. So that's great. Then what we needed to look at was our wet strengths. And you can see at 2%, our wet strength was really poor. We were way down here. If you looked at your TSR, we were here at 0.6. At 2.3, our TSR was 0.89. And at 2.6, our TSR was 0.94. So of course, in this case, we chose 2.3 because it uses less binder. Therefore, it's a more economic mix. And we had plenty of wiggle room with performance. We were all the way up here at 50 PSI in this case, 0.89 on our wet dry strength ratio. Now, VDOT standards have since changed. 53 PSI is the minimum ITS. If you're doing the Marshall stability, it's going to be 2945 pounds via the ASTM method or 1475 on AASHTO. Retained is still 70% or 0.7. So as we round this out, you need to make sure that you consider all of the critical pieces of information. So make sure you look at your gradation, your density, your optimum moisture content or water content, your recycling agent properties such as temperature, water content, half-life, expansion ratio, your recycling agent content, so how much are we going to put in, your active filler content, and also your wet and dry strengths. These are things that I would want at least internally reported, and I'm sure that the agency you're working for will want some of this information as well. So it's very good to have on hand. Make sure you're recording all of this. So with that said, I appreciate your time. And if you have any questions, feel free to reach out to me or reach out to me through the VAA, through Trenton or Mike or someone like that. So thank you. I hope this has been very informative, and I appreciate you having me to talk about this today.